So chlorofluorocarbons, it turns out, are not the only ozone depleting chemicals that humans can put into the atmosphere. Other chemicals that contain bromine, fluorine is already in bromine, fluorine, and nitrous oxide can also have this effect on the ozone layer. What happens is that a chemical that contains chlorine or bromine or fluorine or even nitrous oxide, what happens is those chemicals break down in UV light when they get up into the stratosphere. Notice here with the chlorofluorocarbon, when UV light hits it, one chlorine breaks away. That chlorine then doesn't want to stay by itself just by its nature, its chemical nature, and so it will bind to one of the oxygens in ozone. Ozone, as you may remember, is O3. So if chlorine binds to one of those oxygens, that leaves chlorine monoxide plus oxygen. So there's therefore no more ozone. This is what caused the breakdown of the ozone layer, and therefore more UVB and UVC rays were getting through. So as we're going to see a little bit later, the Montreal Protocol, for the Montreal Protocol, lots of countries got together to discuss this and come up with solutions because they recognized that the ozone layer was a really important thing that we needed and that we were going to see increases in skin cancer if we didn't stop this depletion of the ozone layer. And so because of that Montreal Protocol, the production of chlorofluorocarbons was halted. And the ozone layer stopped dramatically decreasing. However, as I just mentioned, there are other compounds that can cause this deleterious effect on the ozone. And so now the most abundant ozone depleting chemical is nitrous oxide. You may remember that nitrous oxide is one of those greenhouse gases that has increased exponentially since the Industrial Revolution, and it comes from using nitrogen fertilizers on crops and plowing them. So we do still produce some ozone depleting chemicals. Now at this point I want to make it really clear that ozone depletion and climate change are two completely separate issues, both caused by humans but completely separate issues. Ozone depletion is caused by chemicals that bind with ozone and break up the ozone layer, as we've just seen. Climate change, you spent 2 weeks learning about. It's due to the increase of greenhouse gases, which then increase the greenhouse effect. Totally different. Ozone depletion does not cause climate change. The only thing they have in common is that some of the chemicals that are greenhouse gases can also cause ozone depletion. So chlorofluorocarbons can be greenhouse gases. They also cause the ozone to be depleted. Nitrous oxide is a greenhouse gas, but can also cause the ozone to be depleted. But ozone depletion and climate change, other than having similar gases that can affect them, are not connected. So scientists realized pretty quickly that there was a rapidly increasing hole in the ozone layer, and it was largest over the Antarctic. They saw that the ozone layer declined by half in a single decade. And so that really alarmed them. Knowing that the ozone layer was important, that really alarmed them, and it led to pretty rapid action. Another thing that was noticed is that the hole in the ozone changed size based on which season it was, and it is largest during the spring. So what happens there is that during the spring in the Antarctic, the sun is most direct in the Antarctic, and that increases the reaction between chlorine and ozone, leading to a bigger hole. Okay, so we figured out this hole, and we knew what was causing it. And so what happened after that was the Montreal Protocol, as I mentioned. Now I'm going to come back to that a little bit later, but first I want to talk about our last secondary effect of air pollution, and that is smog. Okay, so smog happens mostly in cities because there are more emissions coming from cities, especially from vehicles. Smog is a combination of several different air pollutants. In fact, most of the air pollutants, plus a few others that the EPA monitors, contribute to smog. So here we see those listed. We have nitrogen oxides, carbon dioxide, carbon monoxide, soot, which is particulate matter, mercury, we have sulfur dioxide, and volatile organic compounds. These combine to form tropospheric ozone. Remember, there are two types of ozone, stratospheric ozone, which is the ozone layer, and that's good, and tropospheric ozone, which is down in the troposphere around us, which is bad. It can cause all kinds of respiratory problems. So smog is a combination of that tropospheric ozone as well as many other harmful chemicals. Environmental conditions can make this worse. And health effects that this can have, they can be minor or they can be major, and that depends on the individual and as well as kind of length of exposure. So minor health effects include headaches and nose and eye irritations. Major health effects include asthma, COPD, which is chronic obstructive pulmonary disease, and permanent lung damage. Additionally, in places where you that get a lot of sun, and especially those places that get a lot of sun and are located in valleys, so that includes places like Los Angeles and Mexico City, which are what these two pictures are showing, you can get what's called photochemical smog, where the solar radiation that's coming through from the sun causes additional chemical reactions, and this can be even more harmful. So smog is something that a lot of cities deal with, and it can become worse depending on environmental conditions as well. Okay, so now for the good news. Air pollutants have declined since the Clean Air Act that was passed in the 1970s. So what this figure on the right is showing us is, here we have VOCs, volatile organic compounds, nitrogen oxides, particulate matter, and carbon monoxide. Notice that since 1970, there's been a 73% reduction in VOCs, 41% reduction in nitrogen oxides, 50% reduction in particulate matter, and 62% reduction in carbon monoxide. I'm going to go back real quickly to the first slide because there was another figure that was more inclusive on there. So we're going to go back real quick, right here. This shows the percent change in these things from 2000 to 2010. So this also shows a reduction, and more recently, in carbon monoxide, almost 55%, ozone, lead, nitrogen dioxide, so nitrogen dioxide. We have particulate matter 10, particulate matter 2.5, and we have sulfur dioxide. All of those have decreased even more in recent years. So that's really good news, and we haven't seen a lot of that in this class so far. So what I want you to think about, I'm going to go back forward here, is I want you to kind of remember that air pollutants have been reduced, that the United States has done a great job of reducing air pollution. That doesn't mean it's gone, and it doesn't mean that we should stop doing what we're doing. In fact, it means we should keep doing what we're doing, but it's good. Things are looking good. The other thing to keep in mind is if we look at other changes that have occurred since 1970 in the Clean Air Act, the population has increased, the number of people working has increased, the GDP has increased, the number of drivers has increased, the number of vehicles have increased. So the fact that air pollutants have declined, even though we've had economic increases and increases in drivers and vehicles, shows that efforts really have been very successful. Now, one of the reasons that air pollutants have been reduced is that people recognize that they want clean air and they don't want health issues due to air that is not clean or air that is polluted. And so social demand has largely driven the reduction of air pollutants. I think the other thing is that people recognize if they have health issues. They direct health effects will always cause social demand to increase. The other thing that's happened, and we're going to talk about the Montreal Protocol in just a minute, is that technologies have improved pretty rapidly in order to reduce air pollutants and keep them low, and largely that's been driven by legislation. So laws that have been passed. Okay, so now we'll talk in more detail about the Montreal Protocol. So when the ozone layer depletion was recognized, countries all over the world realized that this was a problem and something needed to be done to stop the depletion of the ozone layer. So in 1987, people from 196 different nations got together in Montreal and they formed the Montreal Protocol. And in this protocol, it was mostly for to cut the production of chlorofluorocarbons, but other air pollution type issues were addressed. So the initial protocol came about in 1987. However, there were later increases in the timetables. So we're going to speed up our timetable. We're going to speed up our reduction in chlorofluorocarbons. The cuts got deeper over time, and cuts in other ozone depleting substances were also made. It is possible, so it was possible and still is possible for certain countries to ask for exemptions, or I guess any country to ask for an exemption. And they have to show that there's no alternative. So for example, the United States still is allowed to use something called methyl bromide. There's that bromine in there that can be an ozone depleting chemical. And they use that as strawberry and cured ham pesticides. What they've shown is there isn't an alternative, or an alternative that isn't as good yet. However, the good news here is I think they are starting to come up with some additional things, some different things to replace the methyl bromide because its use is going down still. Okay, so the Montreal Protocol had huge effects. So nations got together, they made these decisions, they were strict about them, and there was an effect. So over here, look at the effective stratospheric chlorine from 1980 to 2100. After the Montreal Protocol, the stratospheric chlorine coming from chlorofluorocarbons stopped increasing exponentially, but it did continue to increase. And so countries got together again in London in 1990 and caused a further decrease, although it was still going up. And so again in Copenhagen in 1992, when nations got together and set even stricter guidelines, and at that point now the chlorine levels, concentrations have started to decline even further with Beijing, and now we're very close, if not right at zero emissions of chlorine. And so stratospheric chlorine has declined due to concerted and increasing efforts of nations coming together. As far as the hole in the ozone layer, so notice in 1979, no hole, and then that hole got larger and larger. In 1987, that's where it was peaking. So notice, think about what would have happened, what could have possibly happened if nothing had happened. Perhaps that ozone layer or ozone hole would have continued to increase. But what we saw was a quick decline. Maybe it went back up, and then we see these changes. It is higher than it was in 1987 for much of this time, but it is starting to go back down. And the reason for this is that chlorine doesn't go away right away, and its effects aren't going to go away right away either. So we do still have a hole in the ozone layer, but it does appear that the size is decreasing, again, due to direct effects of the Montreal Protocol and later decisions by